Yeah, go ahead, Elizabeth.
Cool. Yeah, hello everyone. So yeah, today I'm going to talk about the most voted on topic, which was how does a compiler work? So yeah, so I guess we'll just go ahead and share my screen. Okay. Can everyone see my screen?
Yeah, I think so.
Okay. Yeah, okay, I guess I'll just get into it if everyone's here. So yeah. So yeah, I'm gonna try writing out stuff as well. So this is gonna be exciting. I haven't really done a presentation like this before, so we'll see. So yeah, to start off, so what is a compiler? So obviously, I think we've all encountered a compiler in our lives. So what is the goal of it? Is to turn a high-level language into a low-level language, or sorry, not a low-level language, but rather like machine code or byte code. So this is either assembly for like a processor or byte code for like a virtual machine or like the EVM or the JVM or something like that. So yeah, so it's just to turn turn a human readable language into one that's not so human readable. So yeah, so inside a compiler are 5 main components. Can I see how this works? I'm using some open source software here, so let's see how this goes. So in a compiler, there's 5 main components. So the first one is the Lexical Analyzer. So this is, so this deals with the tokens in the program. So this is like each symbol, I guess. So in like a C-based language, this would be like if, else, your variable names, like literal values, your brackets, like the types, so like int, void, whatever. So yeah, just like the literal symbols. The next one is parsing. So this deals with the structure of the program. So stuff like matching brackets, whether a statement actually is valid, that kind of thing. And then the next one is semantic analysis. This deals with the actual meaning of the program. So this is stuff like type definitions and what else? Yeah, mostly just like typing. Oh yeah, and if variables are declared and like that kind of thing. So these 3 things are what we refer to as, let's try writing. So these are the front end of the compiler. So the front end is basically turning the high-level language into an intermediate representation for, oh no. Okay, yeah, here we go. So this turns it into an intermediate representation, which is sort of like a language that's in between a high-level one and like a low-level one, or assembly. So it's so intermediate representation is generally like machine independent, but I'll get into this more later. So yes, the next one I guess would be like IR, or intermediate representation generation. And then next one's optimization. So yeah, so this is basically to like optimize the program. So to get rid of like dead code, code that can be simplified, like that kind of thing. There's a lot of optimizations that can be done. So yeah, and then that last one is cogeneration. So actually creating the final machine code that you want to make. So yeah, that is our compiler structure. So yeah, so then this part is referred to as the back end of the compiler. Yeah, so next page. Whoa. Okay, I don't know how this works. This is very confusing. Okay, I guess I'm just going to, how do I make a new page? Sorry, yeah. Okay, there we go. Open source. So yeah, so I guess I'll get into the first part, which is the lexical analysis. So say you have, okay, so the goal of lexical analysis is to divide your program. Oops. So it's the lexical analysis. So I'll try to write better. So the goal is to divide your input program into tokens. So say you have something like this. I'm sorry, this isn't real. Let me try this again. Something like this, like if then like x equals 1 or something like this. So then this turns this into if left bracket x double equals y right bracket, etc., whatever. So basically, yeah, all of these things are one token. So like, yeah, one symbol is one token. So yeah, so at this stage, this is where comments get eliminated, and macros and stuff have already been dealt with at this point by the preprocessor, so it's just in this kind of form. So yeah, so the token analyzer, so the only thing that's really checked for validity at this point, or the only thing that could go wrong, is if you have an invalid token. So something like I don't know, like this, like if it's not defined in your language, like those brackets, and then like a variable with like a number in front, like 0x or like 7x. You can't like declare this isn't valid. So yeah, so those are the kind of things that could go wrong in this stage. Usually it's pretty straightforward. So yeah, so what the analyzer actually does is it reads one token at a time, or sorry, it reads one character at a time, and then say it's reading like the I, and then it reads the next character as well to see whether it should start a new token or not. So say you're reading like I, and then you see the next one's F, you would be like, okay, this is token now. So you're reading the F, and then you see space, new token. Braquish, you know the bracket is its own token, so you would just say, yeah, this is a token. And then same for the variable names, the double equals, etc. So the way this kind of happens in the actual implementation is through regular expressions. So this is a pattern which matches like a specific token. So so stuff like if, else, like int, double, like whatever. These are all like function keywords. So the regular expression for this is literally just like the word itself. So yeah, it's not that exciting. Same for like the brackets. The regular expression is just the literal bracket, semicolon, whatever, same thing. So yeah, but then for something like the variable name, yeah, so then for something like a variable name or an actual like literal value, it would be something like this. So this is uppercase, sorry, and then A to Z. So yeah, oh my God, so hard to write. So yeah, so what this basically says is the first character needs to be an uppercase or lowercase letter, and then the following characters can be letters or numbers. Oh yeah, and probably like underscore as well as allowed. So yeah, and then the plus means one or more, I believe. Yeah, so this is kind of what it would be for variable name or function name or whatever. So yeah, that's exciting. And then for an integer, it'd be something like this. So you might have a sign if you want. And then you can have one or more digits. So yeah, that's basically it for the lexical analysis. Yeah, just basically inputs your code, outputs your list of tokens. So yeah, not super exciting, but it's a thing. So yeah, so there's if you want to like look into this more, there's some open source software that does this. So there's something called Flex, which will take a lexical like specification, so basically a bunch of regular expressions, and then it will turn it into a lexical analyzer in C. So yeah, insert next page. Okay, yeah, so next page. So yes, the next one is the parser. So this is kind of where it gets a bit more fun. So the goal of the parser is to make sure that the program is structurally well formed. So this would be stuff like missing brackets. So like if you only have this, then you don't have your other closing bracket. Like an incomplete like assignment, an incomplete statement, like anything that's just like not valid. So something like this, like x equals nothing. Like yeah, or like int x equals, this can also, like something like this. This can also be, yeah, this is not an int. So this can also be, what's it called? Caught by the parser. I think it depends on the language. Some languages accept this, others don't, but it can be caught in the parser. So yeah, so the parser deals with the syntax of the program. So this is the structure of the program. Yeah, so how is the parser implemented? So this is where it gets kind of interesting. So parser is implemented using something called a context-free grammar. So this is like a set of rules, basically. So one, it's kind of hard to explain. So I'll just do an example. So this is what context-free grammar looks like. So this is your non-terminal. I'll explain what this is in 1 second. And this can be a string of terminals or non-terminals. Or non, oh my gosh. So an example of this would be something like, so you want to have a rule for a digit. So a digit would be defined by 0 or 1 or 2 or 3 or etc. up to 9, obviously. So then this would be your rule for a digit. And then for an int, so say your rule for an int would be something like, okay, let's rename this, or I'll just leave it. It would be something like int smushed with digit. I guess I could do like a concatenation or something to make it clear. I don't know if that's clear or not, but yeah, they're basically just put side by side. Or digit or empty. So okay, so you have your digits. So you want to determine what an int is or what's an int. So you could start with, say, so start with something like, I don't know, so you have 12. So you want to see if this is an int or not. So start with int, go with int, I need another page. I'll just erase some of this. I'll just do it on another page. Okay, so I guess this is kind of more confusing. Eraser. Okay, there we go. Okay. So yeah, okay, I'll go up here. So save something like 12, then you go int digit. So then you can replace digit with 2. So you would say like int 2, and then you can see in the rule that int is also can be defined by digit. So you would replace that with digit. And then digit can be 1. So it says 1, 2. There you go. So yeah, that's how it works. Then something like 1.1, this would not fit the rule because there's a dot. Dots are not allowed in this rule. There's no dots anywhere. So you would know that it's not valid. So yeah, so that's kind of how an example of a context-free grammar. So basically the entire language structure is kind of defined by these rules. So another example would be like the parentheses. So just do something like this. So statement can be statement beside each other, or statement brackets, or empty. So it's so how this would kind of work is, so you have this. So you can do S. S can be replaced with this, and then S can be, so the empty here, or so the S here can be replaced with empty. So then it becomes this, which is matching brackets. Yay! And then something like this obviously doesn't match, so you could try to do it. But yeah, you would see that like you just can't. Like, yeah. Yeah, there's just like no, yeah. So you can tell that, whoops, you can tell that there's basically just like no way to do it. So yeah, so that's how, so if there's something in the language, in the code that doesn't match any of these rules, then you would just like throw a parser error and be like, this is not good, don't like it. So yeah. So next page. So let's see. Okay, yeah, so I guess, see, I'll talk about the parser, the tree, I guess. Yeah, okay, so say you have something like a rule like this. You have your expression, and this can be, you can do expression plus expression, expression times expression, brackets expression, or an identifier. So this would be like an actual like variable name. Oh, sorry, I didn't explain in like the very first slide, like what the terminals and the non-terminals are. Okay, so something like this is a terminal, or sorry, non-terminal, because you can replace it with something else. And then something like this, an identifier, is a terminal because you can't replace it with anything. Like once you get to this point, it is like whatever the variable name is. And same with this. The star is a terminal because it's like a star. It's like, yeah, it's really like a literal that you can't really replace. Same with this, and same with like the brackets. So yeah. So okay, so say we have this string from our token analyzer. So so if you try to generate the tree from the leftmost side, so so this tree is basically an abstract syntax tree. So this deals, so the tree is, it starts at the top with, okay, it's hard to explain. I'll just draw it. Okay, so you start with E. So we're trying to make this into an AST. So you start with E, and then you would do E times E, because we got a times in there. So you start with E at the top of the tree, and then the next one is E times E. So yeah, so the tree, basically for each non-terminal, there's stuff coming, it has some children, and then, or not children, because it's not really directed, but yeah, I guess it has some children, and then it keeps going until it reaches a terminal. So all the leaves in the tree are terminals. So once you have your E times E, you can do E times, then you can replace this E with an E plus E. So then E plus E. And then now you can start replacing with ID. Whoops. So this becomes ID. And then I'll just replace it all in one line, whatever. So yeah, then this all becomes your IDs. So this is what the AST would look like for this statement or expression in your code. So yeah. So basically the entire program is defined by this. So you would have something like, so the start of your program would be defined by like a scope. The scope goes into some like declarations or something. I need to, yeah, it's hard to write out. Oops. Oh, okay. Okay, yeah. So it'd be something like scope, and then this goes into like some declarations. Declarations can be like a bunch of statements. Yeah, and then statements can be like one statement. This isn't like, I don't think this is correct for anything, but statement, and then you have some like expressions. I guess you can't really have expressions, but you can have like other sort of stuff like ifs, like else's. So you have like an if statement. Yeah, so yeah, so that's mostly it for the parser. Like the main thing is turning the entire program into a tree like that. So yeah, I feel like I was gonna show something, but maybe not. Okay. So yeah, so the way the parser is actually implemented, so you can do it either top down or bottom up. So bottom up would be something like this. So you start with, I'll just do IDs again. So it would be something like this. So you start with the statement, and then you would turn it back into your grammar, make sure it fits, etc., etc. And then top down would be like the other way. So yeah. The issue with top down is sometimes that your grammar is recursive. Like for example, this one that I showed earlier, this is recursive because there's the same non-terminal on both sides. So it could theoretically just, yeah, go on forever, or well, not go on forever, but it could be ambiguous in how the tree is formed. Like you could actually form it like one of two ways. So if you're going to do a top-down parser, you would want to eliminate that ambiguity in how the tree would look before proceeding to the next step. So yeah, yeah, what did I want to do? I guess maybe I could show, I guess there's something I wanted to show, but I guess I didn't really explain it right. So I'll show you anyways. So, so yeah, I guess I'm just gonna go over like what is a statement versus what is not a statement. So, or yeah, just like weird parser things. Maybe not too weird, but let me save this somewhere. Okay, I'll put it here. Code.c. Is this like readable or? I don't know, are there any questions thus far? I feel like I just maybe unclear with some parts.
I can see it, it's fine.
Okay, cool.
Yeah, I think everything's been really clear. I think I've been doing a great job.
Really? Okay. I feel like I could have more
Yeah.
code examples, but
yeah, we can also see what you're doing on the screen.
okay, cool. Yeah. So yeah, so something like so you have your int x, you have your int y. Something like this is so these are all statements. So a statement is basically like one line. So something like this is actually allowed. So just see code.c. So yeah, this compiles fine. Terminal's kind of small. Let me make it bigger. Oh. Okay, yeah. So yeah, something like this is a statement. So for like an if, for example, you would have something like if brackets statement. Because I'll just write it out. So yeah, you'd have something like, so if like if statement could be defined by like if brackets and then statement and then a scope and then some other statements in the scope. So yeah, so something like, oops, and then something, yeah, so a statement is just like this. So a valid line would be like statement plus semicolon. And what else? Something like this, like just, whoops, something like just a variable on a line, also valid. Yeah, just like, cause it's a statement in itself. What else? And then stuff like so yeah, this is like a print. Printf is like a statement, returns a statement, that kind of thing. Yeah, return statement. Sorry, I guess I should have said this is actually not a statement. This is an expression. But it's a statement when you add the semicolon. Yeah. Not super exciting. So yeah, I guess I wanted to also show some of the typecasting stuff. So then, yeah, so the next stage is the semantic analysis kind of stage. So for, yes, this is all Gucci, even though it looks a bit funny. So the semantic analysis stage deals with the meaning of the program. So this is, so if you have if you don't declare your variables right, the parser will say this is okay, because, I mean, yeah, so this is obviously allowed, just like X, but if you do this, not good, because it's not declared. So, yeah, so this is not a parser error. The parser is actually like totally fine with this, but the semantic analysis stage deals with that, as well as like scoping stuff. So say you declare your int x in another scope, yeah, not allowed, because now it's undeclared as well. So yeah, so it deals with also types things. So all of the types are mostly defined in this stage. So so x is obviously an int, but say you do like 1.0 or something, it's allowed because the semantic analysis would just say, let's just treat this as an int. Yeah, what else? So, okay. So yeah, okay, so I'll just go more into this. Okay, so yeah. So yeah, like I said, the parsing only deals with the structure, but then this deals with the meaning. So like there's like lots of like natural language examples of this, like something like the dead bird just flew by my window, or like something like that, or like it was really bright, the sun was really bright last night, or something like that. Like this is all like these are all things that grammatically make sense but don't actually meaningfully make sense.
Who?
So
Who's Aaron Jack?
sorry. Okay.
You're muted. Yeah.
Okay. Sorry, but yeah. So yeah, just stuff like that. So yeah, there's a lot of interesting, I guess, or natural language parallels to the compiler. So yeah. So yeah, so there's type checking, like function call params, like making sure they're right number and type, definitions, and then if your language doesn't allow definitions, then checking for redefinitions as well. I think this, yeah, so yeah, C doesn't allow redeclarations. I think Rust does, but Go definitely doesn't like it. So yeah, so it deals with that kind of stuff. So the first thing, whoops. So the first thing would be scope checking. So this checks that everything is declared in a certain scope. Okay, so say you have some code like this. Then you have your int x, and then you have a scope, and then you say x equals 7 or something, and then whatever. Yeah, this is it. So this is actually totally allowed. It looks funny, but so yeah, so in the parser, the brackets are defined as one scope. So you can actually just do like straight up, whoops, no redeclarations. Yeah, so something like this, just like making a scope is totally fine. Making lots of scopes is totally fine. I'm not sure. Yeah, this is interesting. Yeah, so making lots of scopes like that is totally fine as well. So yeah, every time so when the semantic analysis is happening, so every time it reaches a bracket, so it will, okay, sorry, I should talk about the symbol table more. So the symbol table is basically some sort of table that keeps track of every variable. Table, I'll say table loosely because it's usually implemented as a stack of maps, or it can be implemented as that. So you have your stack. So then when the compiler hits this first bracket, it'll say, okay, first scope here. So like scope. This is a new map. And then it goes to here, and then it says, oh, int x, cool. And then it puts the x into this map. And then it hits another scope, and then it's like, okay, push another map to my stack. And then it goes here, and then it says, then it looks in its current scope map first for an x, and then it sees that there's no x. So then it goes down to the next map in the stack, and it says here, okay, there's an x declared, so I'm going to use this one. So that's the one it uses. But then if you did, then if you redeclared this here, then what it would do is then push this x as well to this top scope. And then when doing this assignment to 7, it would assign to the first x it finds on the stack, which is this one. And this is also how it deals with redeclarations. So if you do like int x again, here, okay, so yeah, so once it exits the scope, sorry, it pops this. So delete. So I'm gonna do, oof, oh no. So yeah, so once it reaches the closing bracket, it then pops this and just deletes it. It's no longer really needed. And then it goes back down to this one. And then it'll see there's a redeclaration. So then it looks in the map, sees there's already an X. So just like throw an error saying declaration. As well, yeah, so that's how it deals with scoping things. So yeah, so the next thing is typing. So yeah, typing is exciting, I guess. So so there's a few different types of typing. So there's first static versus dynamic typing. So like C, Go, Rust, these are all statically typed. So this is when the types are determined at compile time. So the compiler internally has a type for everything. So yeah, and then dynamically typed is when the types are determined at runtime, not in the compiler. So this means that in a dynamic type language, say you'd have like a let x or whatever, you have a variable x, x's type can change throughout the program, whereas for statically typed, it can't change throughout the program. So yeah, so dynamic would be like Python or JavaScript. Yeah, but for these purposes, I'll talk about static for now. So yeah, so there's weakly typed versus strongly typed. So strongly typed is what's referred to as type safe. So this is when you can't have any implicit type conversions, basically. So weakly typed would say that it allows for type conversion. So yeah, so something like type casting obviously is still type safe because the compiler does know like what the type actually is, but then something like weakly typed is a bit more unsafe, I guess. I'll show you an example. So C is actually weakly typed because you have void pointers and you can assign these to anything. So you see something like this. So you say you have your array. So if you refer to R, it's actually a pointer to the beginning of the what's it called, of the array. So then you can do something like something like this. So you can say whoa, sorry, whoops. So you can do something like this: void my pointer equals array, and now so my pointer is now a void pointer, but array is a char or pointer. So yeah, this is a bit funny. And then you can redeclare this as like another pointer. So say you have like your int pointer or like I pointer or something. And then you basically just like destroy the types. So this is oh, what did I just do? Oh, whoops, my pointer. So yeah, so this is, the types are basically, yeah, you destroyed them. So yeah, so this will treat the data here as if it's an array of ints, even though it's actually an array of chars. So yeah, so say you do like printf. So let's print the first thing in that's now in I pointer. I guess, yeah, let's print also what's in R, which should be 0xff. Yeah, so what is happening here? Okay, so you can see that in the array, okay, this looks a bit funny because it prints out a whole byte, but this is actually, it prints out like a whole, it prints out like a whole int instead of like just one byte. Whatever. Anyways, yeah, so the int pointer so the int pointer has, okay, this is more confusing than I thought it would be. Okay, so you can see that the data in the int pointer actually changed apart from the last two characters, which is referring to this. So the int is, an int in C is 4 bytes, so which is why it prints out 4. But it's actually, the data in it has only been declared for 1 byte, but it prints out 4 bytes. But it's down to do it because, I mean, it's down to do it for the char array too, but but yeah, it's down to do it anyways, and it thinks it's now an int. So yeah, that's a bit of excitement, I guess. So yeah, another thing that the compiler also does is, so it also deals with type inference. So if you do like int x or like int z equals 1.0, like it will treat this as a 1. If you do something like, let me think. So say you're comparing like a double. So we make a double, 1. And you have a float, so you make a float as well. And then you compare these two. So D equals F. So what actually happens in the compiler is that one of these types takes precedence. So I think generally double has, so there's a type ranking, and then if you compare two things of a different type, it'll decide which one's ranked higher and then just cast both of them as that, basically. So in this case, a double, so let's see. So I think in this case, the double would take precedence. This would actually evaluate to true because it would turn this into a double. So let's see. Okay, it's not true. Okay, well, does it make it, does it turn them into floats? No, that doesn't make sense. Or does it? Huh, okay. Interesting. So maybe this works if I do it all as a one-liner. Let's see. Okay, no, it doesn't like that either. But yeah, so what if I do int? Let's see what happens here. This might, oh, okay, it doesn't like it still. Okay, well, there is some sort of way to show that this is a thing. Let's see. Huh, okay. I guess, okay, so I guess this means float takes precedence over int and I guess double. I'm a little long. Okay, well, if float did not take precedence over int, for example, then this would be cast internally as an int, which would chop off this and make it a 1. And it would say it's equal. If we do something like this, I think it will be true. Yeah, so this is now true because I can just cast them both to a double. Yeah, so yeah, well, I wish there was a better example for that. Okay, well, yeah, anyways. So inside the compiler, that's what it does. So yeah, so it just turns them both into the same type before comparing. So yeah, so there's the type ranking. And then if there's a situation when a type conversion isn't allowed, it would just throw an error and say like conversion not allowed. Yeah, I think if you do something like, let me see. Yeah, if you do something like this, it'll throw a warning, but it doesn't do an error. But in some languages, I think this would probably be an error. Just C allows it because it's C. So yeah, so that is the semantic analysis for the most part. So there's, yeah, that's just the scoping and the typing and that kind of thing. Yeah, that's mainly what it deals with. So what time is it? Okay, I'll talk about the intermediate representation stuff. Oh, okay, so I guess I wanted to also show a little bit about what happens when you actually call a binary. So yeah, so the compiler compiles the source code to the bytecode or machine code, but it also often creates a binary, which is sort of like a second thing. So we have our a dot out here. So so the whole point of the code generation part of the compiler is to convert like higher level structures, so i.e. the abstract syntax tree, into actual machine code. So the AST is literally just like a tree with like the root scope as like the entire tree, and the entire program gets like down from here. So then you would have like your declarations, you have like your statements, and then this turns into like int, I don't know, x, like whatever, etc., etc. Your scope, have more scopes maybe if you want more scopes. Yeah, so the entire program is literally just a tree with one root node for the most part. So yeah, so for cogeneration, you want to turn the AST into like assembly. So the assembly also deals with things that you don't have to worry about in the high level language, which is like the memory. So like how are the variables laid out in memory, as well as like what will the runtime environment of the code be. So this is the stuff that's maintained like while the program's running to implement the structures that you need. So this would be stuff like the stack and the heap, and like virtual function tables, that kind of thing. So yeah, so the main question we kind of have to deal with is, first of all, like how is the data organized in memory? And then also where do functions return to as well when they need to return? So sort of how like the subroutines, how do the subroutines look like in the actual code? So this is like the question of control flow. So like yeah, so where do programs return to? So the first thing, so I guess so what happens when we actually execute this program? So this is kind of interesting. So you do this. You do a.out, and then what your compy actually does is it first reads like the first, I don't know, like 512-ish bytes into memory, and then once it reads that, it then looks for this specific marker. So this is 0x7f and then ELF, and then this is like 0. ELF is it's like 0x like 4, 5 for E, something like that. It's just like the actual like ASCII values, I think. So this marker says that this executable is an executable and linkable format. So this is a cross-platform format that is like used in a lot of different platforms, I think. So Unix uses it. So this means that the file contains the data that's needed to set up the runtime environment. So it says whether you're using like whether the code in the executable is for 32 or 64-bit. And then it also says there's also like sections which say determine so in the actual what the actual memory kind of looks like when you run this executable. So you have the address space for this program. This is like the space in, I guess, memory well, yeah, so this is the space that the program's given in memory, so it looks like something like this. So you have your stack, and then at the bottom here you have your heap. So I'll say what's in all of these soon. You have a .bss. You have a .data and a .text. This is really poorly drawn, I'm sorry. Okay, so the stack has your local variables in it. So when you enter new scope, your variables go in there. The heap would be your, or like your dynamically allocated variables. Some more variables. Then your BSS is 0 initialized static variables. So this would be something like this, for example, is like 0 initialized. And then the .data is non-zero initialized vars. And then, so like the int x, non-zero initialized would go in there. And then the .text is the actual binary. So yes, this is kind of what the memory layout looks like. So let's see. So I had some, I think, some dumps I wanted to show you guys. So let's see. So you can, read ELF is a tool you can use to like read what's in an ELF file. So this is really big right now. Okay, yeah. So this is kind of the magic number, which is like the 0x ELF I was talking about. So it says it's an ELF. So it has some also other data. So we're using Little Endian, Unix, AMD, some extra stuff. So the entry point address, this is like where the actual program is in the binary, I think. So you have your program headers, section headers, like basically, yeah, a bunch of nice stuff in there that says like how to set up the environment. What else? Opt dump shows more. Let's see. Shows more. Whoops. Oh, this is really big. Can you guys still read this? Yeah. So you have a lot
I
of.
think so. Yeah, definitely read it.
Yeah. So this is like you have a lot more sections than I said, but this is like the basic stuff. So you have your .text, which is actual binary. Data, BSS, that kind of thing. And then your nice symbol table. What else? Yeah, I think that's mostly what's in there. I think then if you do .d, it shows you all the actual assembly that's in here. So yeah, so here's our main code. So this is like literally what's in our main. So yeah, I'm not going to explain what all this is because that would be a lot of effort. Yeah, so basically that's what's in your nice binary. So a lot of stuff. Okay, so continuing on. So yeah, so how is an actual, whoops. So a function call is implemented using a stack frame. So the frame contains, let's just say this is like the top of your stack. So say you have a func, so you have foo. And some stuff happens in here. Turn X. And then you have your int main. And then do foo of 1 and return. Okay, so what happens here? So first you go into your main. So you would push a frame main to your stack. And then what's inside the frame is, so you have your function arguments. You have the return address you need to return to. You have the address of the caller frame. So this is, I guess, easier to show when I do the foo one. And then you have your local vars. So that's like, there's no local vars in here. So yeah, and then it would go to foo, get to foo, push a frame foo. So then in foo, you would have, so there would be X, there would be the location of here, basically, because it's the next, or next is the next line after where you have to jump to once this return's done. Yeah, then what else? Then you would have, well, X is an arc, then also becomes local, so you'd have that in there. And then the color frame, so it would also have the location of this, so like this address, it would know about. So yeah, that's basically what happens when you're doing the function call. So how does this relate to the IR? So yeah, so the goal of the IR is to, so this is the intermediate representation. So this is a representation of the code that's in between high level and low level. So intermediate representation is generally machine independent and language independent. So so this maps the source code into a form that can easily be turned into machine code. So it lays out kind of what all the variables are that you need. Like it would turn, okay, I'll just read an example. It's hard to explain. But yeah, so your source code is like this. You have main, and then so you just have like int x, y, z, and then you have like x equals y plus z plus 1 or something like this. So then your IR would be something like this. So you'd say like, so you're defining your function, then you would say begin func. So this is where you start your function. So then you would say int x, int y, int z, and then you would have temp 0. So basically all the lines that are like this, where it's multiple things happening in one line, become separated out into a form where there's at maximum 3 things on the right side here. So this would be y plus z. So you have your two and your two operands, and then your operator. Yeah, that's the right word. And then x equals t0 plus 1, turn 0, and func. So yeah, so this is much more easily translatable into something like assembly, because now this is one reg register. This is line. You can't, yeah, you just like can't do this all in one assembly line. So yeah, so it's just more easily mappable for the most part, as well as easier to optimize it when it's in this form, because it's easy to see where like where you go into the func and where you go out, as well as all the scopes and everything. So yeah, what was I gonna say? Oh yeah, so for something like LLVM, so how LLVM works is that you do your entire front end part. So you would do the lexical analyzer, the parser, and the semantic analyzer, and then you would the output from the front end would be IR, I believe that's readable by LLVM. I'm not like an expert on this, but I believe that's how it works. And then LLVM will do all the optimizations on the IR and turn it into the actual source codes. Then it does the back end part for you. You just have to do the front end. Yeah, so the output from the front end is your AST. So let's say we have an AST like this. Okay, I guess I'll write out the code. So so you have something like this. And so that equals y times 9. Okay, so then you first want to turn this into 3 address code format, which is kind of what I talked about here. So basically how on the right side you can only have 3 things maximum. So yes, this could be either one, what's it called? Yes, you could have, so your allowable things would be something like t1 equals x, this is allowed. T1 equals minus x, this is allowed. T1 equals like x plus y. These are the only things that are allowed in your intermediate representation. So yes, this is called TAC, or 3 address code, because yeah, it only has 3 addresses maximum. So yeah, so then this would get turned into like int t1 is 32, int t2 is 8, int t3 is t2 times 9, t4 equals t1 plus t3, and then int, whoops, how much time do I have? Okay, this is like the last part, so I'll finish after this. So then int t5 is just t4. So then you have your AST. So you turn this into your nice AST. I'll try to do this all on one page. Just have to do a long line. So then you have on this side z equals, so yeah, so this is x equals 32, y equals 8, z equals, so you would do it like this. So you'd have plus x. Okay, I need to erase some of this. Okay, so then you would have on the side. So then x plus y times 39, which would be like this, or y times 9, which would be like this. So then this is your AST for this little snippet of code. I'm gonna change the color. Let's try this. Oh, I feel like such a professor changing the color. Okay, so yeah, so then you would, from the AST, you would generate your 3 address code, and it's pretty easy to do that from the AST. So at each like operator here, you would basically write a line of the TAC. So it'd be like this. So this first one is T1 32, T2 equals 8, and then this is so this one's T3. Yeah, this one's T3 equals T2 times 9. This one is T4. So this is T4 is T1 plus T3. And this one becomes T5, which is now equal to T4. So yeah, this is, yes, this is how you get your intermediate representation from the AST. So yeah, I guess I can show. So yeah, so for, I might as well, yeah, I'll just show it. But for something like GCC, they use an intermediate representation called, well, they use a few, but the main one I think is called Gimple. So this looks something like this. So yeah, so you can see that it does follow the form I said, where each line is kind of one variable, and there's maximum three things on each side, or on the right side. And then yeah, you still have your printf, so that's not gone yet, but I'm sure it will be in the next stage. So yeah, so that's kind of it. For LLVM, I think they have something that makes more sense than this. I haven't looked into it too much, but yeah, would be cool. So Okay, yeah, I think that's mostly it. I had some stuff on optimizations, but I don't know, it's been an hour, so. Yeah, any questions? Anything that was a bit unclear?
It doesn't seem like anybody has a question.
Okay.
But yeah, great talk. It was very informative, especially for me. I know nothing, but it was honestly really cool to see linguistics and semantics being
Mhm.
applied to not just random sentences in English and actually into code. That was pretty cool for me.
Yeah, it's definitely, yeah, linguistics is definitely relevant to, yeah, like computer languages for sure.
Yeah, I mean, so like most of these programming languages can be like not fully expressed, but most of them can be expressed as like context-free grammars. And I think that's like a concept from like the student linguistic. I forgot his name. I think it's like some MIT prof like that studies linguistics, but now he's also technically a computer scientist kind of ish because people use this in computer science now. But I don't think it was originally like written with computer science in mind. But like all that stuff is yeah, it's very very related with like linguistic studies. It's pretty cool.
Noam Chomsky.
Oh right, duh, of course. How did I forget his name?
Oh, that's kind of cool. Yeah.
How did you get interested in this topic? Like, are you making your own language or something, or?
Oh no, I just thought it was interesting, and then you guys voted on it at the poll, so. But yeah, I don't know. I think it's cool. I think it's definitely, yeah, interesting to see what kind of goes on in the compiler, since it's sort of a black box. Like you just like hit run, you just like hit click compile, and then it compiles. But then what's actually happening? Yeah, I don't know. Write my own language would be cool, but maybe not. Maybe not yet. Maybe one day.
How much of that stuff is in the EVM for when it's compiling solidity? Is it totally different things?
Like I'm pretty sure some like yeah like this is what I laid out is like the basic structure of like all compilers for the most part. Like maybe there's like some, I don't know if there's like any that don't really follow this basic form. It wouldn't really make sense for them to not. So yeah, like every compiler does have like these things that I said. So yeah, the Solidity compiler definitely does. But then yeah, like I said, instead of generating assembly, it does like EVM bytecode. Yeah.
Yeah, I'm pretty sure they have like a context-free grammar definition for Solidity somewhere too. I remember seeing it at some point. Yeah. I like originally like Solidity didn't really have like any intermediate representation languages. But I think there is. I think that's what UL is designed to be. YUL. It's like still relatively a new thing. I think. I don't know if that's like widely used as an intermediate representation for Solidity yet. But I think it's like actively being worked on by some folks. I think the goal is originally was like for to compile Solidity to like some EWASM runtime. So if you like develop like some intermediate representation, then you can get that into EVM bytecode or like some EWASM thing. I think that was like the whole idea with all that work. But yeah, it's pretty cool.
Cool. Yeah. Yeah, I didn't get to talk about the optimization much, but yeah, like the point of the intermediate representation is to just have like a sort of machine independent language that can be optimized separately. Yeah, so yeah, that's pretty cool.
Yeah. If no one has any more questions, I think we can wrap up our first ever ChainSafe chat.
Woo!
Woo!
This was really incredible.
Thank you.
Learned a lot.
Cool.
You know, little crap.
Awesome
Okay,
talk.
I'm gonna stop screen sharing. Okay, cool.
Great. Thanks everybody for coming out. This was really great. Thank you. And hopefully we'll
Yeah,
see
thank you.
Yeah.
Thank you. Have a good day, everyone.
Woo.
Thanks. Bye.
Bye.
Bye.